Hello, everyone. I hope you have a truly meaningful story listening experience. Right now, you are probably sitting in a completely ordinary room, a chair, a window, a glass of water on the table. The surface of the water is so still that there is almost nothing worth noticing. The floor is not shaking. There is no sound of an engine beneath you. There is no sensation of wind pressing your body backward. If you trusted only what your senses were telling you, the most reasonable conclusion would be that you are standing still. But that is the first strange thing. You are not standing still at all. If you are near the equator, the surface of the Earth is carrying you around its axis at a speed of about 1,670 kilometers per hour, more than 460 meters every second. That is far faster than the kind of speed our intuition usually associates with a body sitting still in a room. So why does the water in the glass remain still? Why can't you feel that speed? The answer lies in something very simple. Constant motion does not necessarily create the sensation of movement. Think about a flight that is cruising smoothly. Once the airplane has reached altitude and is moving at a relatively steady speed, you can still hold a glass of water. You can sit in your seat and feel as though the small room around you is almost motionless. What matters is not only how fast you are moving. What matters is how you and your surroundings are moving relative to one another. The same is true on Earth. You move with the ground. The house moves with you. The city moves with the house. The oceans and the atmosphere are also sharing most of that motion. In the frame of reference of everyday life, nearly everything around us is traveling together on one enormous train. And precisely because everything is moving together, we call that feeling standing still. The glass of water on the table therefore becomes a rather beautiful symbol for this entire story. Its stillness does not prove that there is no motion. It only proves that the glass, the water inside it, and the room are all sharing the same motion. But the speed of 1,670 kilometers per hour is only true for part of the planet. This is where the story begins to become more complicated. The Earth completes one rotation around its axis, in roughly the amount of time that makes up the familiar day we know. But a person standing near the equator has to travel along a much larger circle than someone standing at a high latitude. In the same amount of time, the person at the equator has to cover a greater distance. That is why their tangential velocity is higher. The closer you move toward the poles, the smaller the circle becomes that a point on the surface has to travel. As a result, the speed gradually decreases. At the geographic poles themselves, your distance from the rotational axis no longer produces any significant circular path, and the tangential velocity caused by Earth's rotation approaches zero. That immediately creates a very intriguing thought. If the Earth suddenly stopped rotating, would the polar regions be safe? They might be less dangerous in one very specific respect. But less dangerous and safe are two completely different things. We will have to return to that question later, because the planet consists of more than just the ground and the people standing on it. First, there is an even bigger misconception that needs to be cleared up. 1,670 kilometers per hour sounds like a terrifying speed, so it is very easy for an image like this to appear in our minds. The ground stops, everyone is thrown off the Earth, and we fly straight into space. But that would not happen simply because the Earth stopped rotating. Gravity is not created by the planet's rotation. The Earth stopping its rotation does not mean gravity would disappear. And the speed at which the surface is carrying us, even at the equator, is still far lower than the speed required to escape the planet's gravitational pull. This is a truth that is frightening in a different way. You could experience a horrifying catastrophe and still never leave the Earth. The real danger does not lie in us flying into space. It lies in the difference between what has just stopped and what has not yet had time to stop. Up to this point, the ground, you, and the glass of water have all been sharing the same motion. There is no major conflict between them. But now, change just one thing. Suppose that, in a single instant, the solid part of the Earth stops rotating. No explosion is necessary. Gravity does not need to disappear. The planet does not need to break apart. The ground simply has to stop. T equals 0. The Earth has stopped, and in that seemingly silent instant, one of the simplest laws of physics becomes our greatest problem. An object in motion tends to remain in motion. In our hypothetical scenario, The ground has just lost its rotational velocity. But objects that are not directly slowed down by this mysterious mechanism still retain the momentum they had immediately before the moment of stopping. 1 second earlier, their shared motion made everything look peaceful. 1 second later, that very same motion creates the difference between the ground and everything resting on top of it. At first, the glass of water seemed to symbolize nothing more than stillness. Now it reveals something deeper. The stability of our world does not come from everything standing still. It comes from countless things moving together according to an order we rarely have to think about. And only when one part of that order is taken away do we realize how deeply we have depended on it. But before we ask what would happen to cities, or what the entire planet would have to endure, we need to begin at the scale closest to us, your own body. If the ground beneath your feet suddenly stopped, while you still retained the motion you had a moment earlier, then in that very first second, where would you actually go? If the ground beneath your feet suddenly stopped, while you still retained the motion you had a moment earlier, then in that very first second, where would you actually go? Let's begin where the answer is most extreme, near the equator. Just 1 moment earlier, you, the ground, and everything around you were moving together around the Earth's axis at more than 460 meters per second. Because everything was moving together, there was no reason for you to feel that speed. But at time 0, the rules change. In our hypothetical scenario, the solid part of the planet comes to a stop. Your body does not. No invisible force suddenly appears at that exact moment to erase the motion you already have. Inertia does not care that the ground has just changed its state of motion. Your body still tends to continue moving in the direction it was traveling immediately before the moment the Earth stopped. And this is the important distinction. The danger does not come from your absolute velocity through space. It comes from your velocity relative to the ground, which has just become stationary. 1 second earlier, you and the ground were barely moving relative to each other. 1 second later, that synchronization is gone. You become a moving object traveling across a surface that has stopped. The initial direction of that motion follows the direction in which the surface had been rotating, usually described simply as eastward. But saying that you would merely be thrown eastward still does not describe the real world. What lies ahead of you is not empty space. There are walls, trees, terrain, buildings, the ground itself, and countless other objects also responding to this change in different ways. That moment reveals something very strange about inertia. Normally, it is one of the laws that makes the world predictable. An object in motion does not simply lose its motion for no reason, but when the familiar frame of reference around us changes abruptly, that same ordinary law becomes the source of catastrophe. However, the outcome would not be the same for everyone. Move away from the equator. At around 45 degrees latitude, the Earth is still carrying you around its axis before it stops. But the circle you travel along is smaller than the one at the equator. As a result, your tangential velocity is also lower, the same sudden stop, the same law of inertia. But the difference in velocity between you and the ground is no longer the same. Now continue toward the poles. The circle of motion around the axis becomes smaller and smaller. The tangential velocity caused by the Earth's rotation continues to decrease. Very close to the geographic poles, the direct inertial effect produced by the surface's rotation could be far smaller than it is at the equator. The same planet, the same moment, but not the same velocity. And that makes the idea of a survival zone begin to sound reasonable. If the initial danger comes from the ground losing its rotational velocity, while your body retains its motion, then the place with the lowest rotational velocity would seem to be the best place to be. That is partly true. But this is one of the traps that intuition will keep setting for us throughout this thought experiment. Less direct inertia does not mean safety. It only means that one of many problems is smaller, because we are still assuming that everything on the surface responds in the same way. It does not. A building is connected to the Earth's crust through its foundation. A tree is connected to the soil through its root system. A vehicle contacts the road through its tires and friction. Soil and rock have different structures and different degrees of cohesion. Water can shift far more easily than a block of concrete. So the statement that everything will keep moving eastward is a useful way to understand the basic idea, but it is not the complete picture. Some objects are tightly coupled to the solid part of the planet and will experience forces through those connections. Others may continue moving longer before friction, collisions, or terrain alter their direction and speed. Large structures do not simply behave like free-moving objects. When the foundation they depend on suddenly changes its motion, forces transmitted through the material can cause those structures to deform or sustain damage. Terrain also becomes part of the story. A flat surface is not the same as a mountainous region. A valley is not the same as a coastline. A densely built city is not the same as open land. In a single instant, your location on the map stops being merely the place where you live. It becomes part of the physics problem that determines how your motion will be interrupted. This is also why we cannot find one single number and use it to describe the fate of everyone on Earth. Inertia gives us the starting point, but friction, structures, and terrain determine what happens next. So let's allow this experiment to be kind to you for a moment. Suppose you happen to be in a favorable location. Suppose the first forces do not strike your shelter directly. Suppose the structure around you is strong enough. Through a rare chain of conditions that is difficult, but not impossible, to imagine, you survive the first few seconds. You are still here. Gravity is still holding you to the planet. The ground beneath your feet has finally come to rest. Inside a sturdy shelter, after the initial chaos, you might for the first time begin to think that you have survived the worst of it. And that moment truly matters. Because throughout this entire thought experiment, survival is not something we should take lightly. But there is a problem. So far, we have only talked about people, buildings, soil, rocks, and things in contact with the surface. We have only stopped the solid part of the planet. Above your shelter is an enormous layer of matter surrounding the entire Earth. It had been moving with the planet long before human beings ever appeared. And according to the same rules we have just applied to your body, there is no reason for that entire mass of matter to suddenly lose its momentum simply because the ground beneath it has stopped. So just when you think you have found a place quiet enough to survive, the question is no longer where your body is going. The question is now above your head. The atmosphere has not stopped. The atmosphere has not stopped. And that changes the entire meaning of the fact that you just survived. In the previous chapter, we temporarily left you inside a shelter strong enough to withstand the first few seconds. The ground beneath your feet had come to a stop. The objects near you had finally begun to lose some of their initial relative motion. For a brief moment, it seemed as though the chaos was starting to shrink. But above you is something we easily forget, simply because we cannot see it. Air seems light. You move your hand through it and barely feel anything. You breathe it in without thinking about the weight of what has just entered your lungs. But when a layer of gas surrounds an entire planet, its mass is no longer something insignificant. The atmosphere is an invisible ocean, and before the moment the Earth stopped, that ocean of air was also participating in the planet's rotation. Not every molecule of gas was moving exactly like the ground. The atmosphere already had winds, convection, and its own weather systems. But on a global scale, it had existed day after day above a rotating surface, exchanging momentum with that surface, and participating in a shared system of motion. Now the surface has been forced to stop. The atmosphere has not. This is where we need to change the way we think about wind. On an ordinary day, when you say the wind is blowing at 30 or 50 kilometers per hour, you are describing the speed of the air relative to the ground beneath your feet. That difference is what you actually feel. In this thought experiment, the ground has just been brought to a standstill, while the air above it still carries the momentum it had before. So the problem is not simply that the air is moving fast. The problem is that the ground beneath it is no longer moving with it. The synchronization that once made the glass of water in that first room appear perfectly still has now been broken on a far greater scale. Instead of one body moving across stationary ground, we now have an enormous layer of gas moving relative to the entire surface of the planet. And the ground is not flat. The air encounters mountains. It encounters forests. It encounters cities filled with structures. It encounters valleys, plateaus, and every irregular feature of the terrain. Every obstacle forces the airflow to change direction. Friction acts against it. Different layers of moving air interact with one another. The flow becomes more turbulent. In places where the difference in velocity is extremely large, changes in pressure could also become extraordinarily violent. That is why a mountain is no longer just a mountain. It is an obstacle standing between a mass of air trying to maintain its motion and a surface that has stopped rotating. A forest is not simply exposed to wind. It becomes a place where momentum is transferred between the air, the tree trunks, and the ground. A city is not merely facing a storm in the ordinary sense. Its buildings, streets, and every part of its structure become part of the airflow problem. The disaster is therefore no longer confined to a few meters around your body. It spreads across the terrain, then across regions, then across continents. But this is where we need to avoid another mistake. The atmosphere would not continue racing around a stationary Earth at the same speed forever. If it did, we would have forgotten one of the very things that made the situation dangerous in the first place. Friction, the ground itself, the mountain ranges, the trees, and the objects obstructing the airflow would gradually remove momentum from it. The air exerts force on the surface. The surface exerts force back on the air. The energy of that relative motion is gradually dissipated through friction, turbulence, and many other complex processes. In other words, the atmosphere is trying to adapt to a new world. But adaptation does not mean gentleness. While momentum is being transferred, the very process of losing that motion could produce some of the most violent chaos of all. And we cannot simply choose one number and declare that after a certain number of hours everything would return to normal. The time required would depend on interactions between the atmosphere, the terrain, and the surface on a planetary scale. What matters more is that the system is not frozen inside the disaster. It is evolving. The first stage is dominated by the enormous difference in velocity. Then friction and the transfer of momentum begin to reduce that difference. If you are still alive inside your shelter, this is one of the first glimmers of hope in this thought experiment. The atmosphere will not remain in its initial state forever. Eventually, the most violent part of this relative motion will weaken. Unfortunately, that still does not mean we can open the door and call the outside world safe. Because from the beginning we have been looking upward, while another system has been lying directly beneath the continents. Air is only the first form of matter we have examined that continues moving. Beneath it lies a mass of matter, far greater in weight, covering most of the planet's surface. It too shared the Earth's rotation before time zero. It too has momentum, and it too receives no special miracle that allows it to instantly forget its motion. And unlike air, it is confined within basins, blocked by continents, forced through straits, and driven directly against coastlines where billions of people once built cities. If the atmosphere is an invisible ocean, then now we have to face the real ocean. And the ocean has not stopped either. If the atmosphere is an invisible ocean that continues moving above us, then directly beneath it lies a much larger mass of matter. Water covers most of the Earth's surface, and before the moment the planet stopped, that entire system also existed on a rotating world. So the first intuition comes easily. A massive wall of water races around the planet. A global tsunami sweeps across every coastline in the same way. That is the simple image. It is also a very cinematic one. But the ocean is not a perfect bathtub. The water on Earth does not sit inside a round basin with a flat bottom. It is divided by continents, islands, peninsulas, and narrow straits. Depth varies from shallow coastal waters to trenches several kilometers deep. Beneath the surface are continental shelves, underwater mountains, mid-ocean ridges, and basins with completely different shapes. That means that when the ground stops but the water retains its initial momentum, we do not get one single wave with one single outcome. We get millions of bodies of water, all trying to continue moving in a world where every boundary around them has suddenly changed its state of motion. Imagine that you live near a coastline. Immediately before time zero, the offshore water and the seafloor beneath it were both participating in the planet's rotation. When the solid part of the Earth stops, the seafloor becomes an obstacle to the mass of water that still carries momentum. From that moment on, the question is not simply how fast the water is moving. What matters more is what it encounters along the way. Every coastline becomes a boundary condition. Every chain of islands becomes an obstacle. Every ocean basin becomes a different problem. In one place, the water may collide with a broad continent and be forced to change direction. Somewhere else, it may be squeezed through a strait. Part of the energy may be transferred onto land. Part of it may be reflected back. New movements may collide with other movements and create secondary waves. So, the coastal disaster would not look the same everywhere. A steep coastline is different from a low-lying plain. A narrow bay is different from an open coastline. A city only a few kilometers from the sea, but located on high ground, would face a different situation from a city built on low-lying land that extends far inland. In areas where the terrain allows it, water could travel much farther inland. Elsewhere, the landscape could limit its path or force the flow to change direction. There is no single line on a map that could tell us that everything inside it would be safe while everything outside it would disappear. This is where the image of one single tsunami becomes far too simple. An ordinary tsunami begins with a major disturbance in the ocean, after which energy travels through the water. In our thought experiment, the frame of reference of the entire ocean has just changed. The water has not simply received an impulse at one point. A global system is losing synchronization with the sea floor beneath it. Different basins would respond differently. Their shapes could cause certain motions to be amplified or sustained longer through resonance. Waves reflected back and forth could collide with one another. Energy would be transferred, dissipated, and redistributed through a system far more complex than a single wall of water traveling once around the world. But just like the atmosphere, the ocean cannot remain in its initial state of chaos forever. Water strikes the seafloor. Water strikes the coastline. Currents interact with one another. Friction, turbulence, and countless collisions continue to drain energy from the relative motion. Over time, the most violent movements would weaken. This is an important point, because our thought experiment is not the story of a planet permanently trapped in the first second of disaster. Physical systems are always moving toward a new state. If a group of people could survive long enough, there would eventually come a time when the ocean was no longer moving with the intensity of those first few hours. The most turbulent waters would gradually lose energy. A new kind of stability would begin to emerge. And that may be the first piece of good news the ocean gives us. The chaos does not last forever, but the return of calm does not mean the old world returns with it. This is the most important turning point in this chapter. Until now, we have kept asking how the water would move immediately after the earth stopped. But eventually, that question would no longer matter. Another question would replace it. After the water loses most of its initial relative motion, where will it settle? There is a reason the oceans have the shape and distribution we are familiar with today. The Earth is not a perfectly spherical, motionless object with water simply resting in the lowest places. The planet is rotating, and that rotation contributes to the equilibrium of both the Earth's shape and the surface of its ocean. Throughout our lives, we look at world maps as though the oceans and continents were fixed outlines. The Pacific is there. The Atlantic is there. The coastlines seem to belong to the planet itself. But a coastline is not a promise. It is simply the place where water and land meet under the current state of equilibrium. If the conditions that create that equilibrium change, the location of the water can change as well. So surviving the first waves still does not answer the most important question about the ocean. Just like the glass of water in that first room, the water will eventually try to find stillness again. Only this time, the place where it finds that stillness may no longer be the place we once called the sea. When rotation disappears, the map of the planet must change as well. When rotation disappears, the map of the planet must change as well. But to understand why, we have to let go of one very familiar image of the Earth. The Earth is nearly spherical, but not completely. For billions of years, this planet has not only been shaped by gravity, it has also been rotating. That rotation helps produce the bulge around the equator and makes the distance from the Earth's center to its surface different from place to place. The difference is very small to the naked eye, but on the scale of an entire planet, it is large enough to become part of the equilibrium that the oceans, the atmosphere, and the solid Earth itself have adapted to over immense spans of time. In other words, rotation does more than carry us around the planet's axis. It helps shape the world we live on. And the moment that rotation disappears, one of our most familiar assumptions also begins to change. Sea level. We usually think of sea level as a fixed line on a map. Below that line is the ocean. Above it is land. But nature does not draw that line. Sea level is the result of water settling onto an equilibrium surface under the influence of the Earth's gravitational field and the planet's rotation. It is close to a surface where, if water were free to move long enough, it would no longer have any reason to flow preferentially in one particular direction. That real surface is not perfectly smooth either. The Earth's gravitational field is not exactly the same everywhere, and the equilibrium shape that water follows is more complicated than an ideal sphere. We often use the concept of the geoid to describe an approximation of that surface. And this is the important point. If rotation disappears, the new equilibrium surface will no longer be the same as the old one, so the water must redistribute itself. But do not imagine the entire ocean simply rushing straight toward the two poles like water draining into two enormous holes. That would still be too simple. The topography of the seafloor, the shape of the continents, the actual gravitational field, and the Earth's own adjustment process would all contribute to the final result. What happens during the first few hours would also be very different from what happens after many years. At first, the ocean responds violently because of the momentum we saw in the previous chapter. That is a problem of motion. But as the large relative motions gradually weaken, another problem begins to dominate: equilibrium. The water is no longer mainly answering the question of how fast it is moving. It begins answering a much slower question. Where is the lowest place in this new world? And the answer could leave familiar coastlines far from where they once were. A region that once faced the ocean might no longer stand beside the same shoreline. An area once considered inland could find itself in a completely different relationship with the water. The maps that civilization once relied on to locate ports, cities, and places to live would no longer be permanent descriptions of the planet. But even this is not the deepest layer of change, because up to this point, we have still been treating the solid Earth as an unchanging mold that the water must adjust around. On human timescales, that seems reasonable. Rock is hard. A mountain does not change shape in a single afternoon. A continent does not soften over a few years simply because the physical conditions have changed. But a human lifetime is a very short period of time for a planet. Over sufficiently long timescales, material inside the Earth can deform. The crust and mantle are not an absolutely rigid sphere of rock that remains forever in exactly the same shape. They can respond slowly to changes in stress and gradually move toward a different configuration. This is where the time scale of the story expands. We began with 1 second. Then came the chaotic hours of the atmosphere and the oceans. Now we have to think in centuries, and even in geological timescales. The solid part of the planet could also gradually adjust. Not suddenly, not according to a simple map that we could draw precisely in just a few sentences. That process involves the way the crust, mantle, and the Earth's entire structure respond as a system that behaves elastically over some timescales, but can deform slowly over others. And here, uncertainty becomes important. A thought experiment does not give us the right to pretend that we know exactly where every future coastline would lie. What science allows us to say with greater confidence is that the present equilibrium formed on a rotating Earth. If rotation is removed, both the water and the solid part of the planet must confront a new equilibrium state. What is remarkable is that after all that chaos, the Earth would still tend to seek stability again. Not the stability we know, but a new kind of stability. The oceans might stop moving violently. The rocks could adjust very slowly. A new map could gradually take shape. And if human beings were still alive to see it, it would be a strange moment. We might stand on the same planet beneath the same sun, while the outlines we once considered permanent features of our homeland had become memories. However, there is a larger problem. Suppose the water has finally found its new equilibrium. Suppose the new coastlines have stabilized. Suppose the most violent part of the redistribution process has ended. We still would not know whether that world was a place where human beings could live outdoors. Because a map only tells us where the land and water are. It does not tell us where the rain will fall. It does not tell us how heat will be transported. It does not tell us where the planet's enormous air currents will go when one of the forces that shaped them throughout the entire history of civilization no longer exists. We have changed the shape of the seas. Now we have to change the way we think about the sky. Because every wind we know was born on a rotating world. Because every wind we know was born on a rotating world. That is what makes the next step of this thought experiment more difficult. We have given the oceans time to settle. We have imagined that a new map might gradually emerge. But even if land and water find a different state of equilibrium, the atmosphere still has to perform the task it has carried out since long before human beings appeared. It has to transport heat. And to understand how it would do that, we first need to understand a term that often makes things sound more complicated than they really are: the Coriolis effect. Imagine standing on a giant rotating disc and trying to throw a ball straight towards someone standing on the opposite side. To an observer watching from outside, the ball continues along its natural path. But to the two people rotating with the disc, the path of the ball appears to curve. No invisible hand is pushing it sideways. What has changed is the rotating frame of reference of the observer. The Earth works the same way. Air moving north or south across a rotating planet also carries the momentum associated with the location where it began. When it reaches a different latitude, the surface beneath it does not have the same tangential velocity as the place it came from. As a result, within a frame of reference attached to the Earth, the airflow appears to be deflected. The strength of that effect is not the same everywhere. Near the equator, it is weaker. The farther you move toward higher latitudes, the more noticeable its role becomes. This is not just a minor detail from a textbook. It is one of the reasons large-scale air currents do not simply flow in straight lines from hot regions to cold ones. It helps shape the way the atmosphere organizes itself into the patterns we have come to recognize as normal weather. And now we have removed rotation. So the Coriolis effect nearly disappears from our new problem. That leads to a very understandable intuition. Without the Coriolis effect, would the air eventually become still? No, because the Coriolis effect is not what creates every wind. Even on a non-rotating Earth, the sun would still heat the surface unevenly. One region would receive more energy than another. Land and water would still absorb heat differently. Warm air would still tend to expand and become less dense. Cold air would still be denser. And when temperatures differ, pressures can differ as well. The air would still have reasons to move. Differences between high pressure and low pressure regions would still exist. Convection would still occur. Water vapor could still rise, condense, and return to the surface. Water would still have to move through the hydrologic cycle, so the new world would not be a planet without weather. It would be a planet whose weather is organized according to different rules. This is a very important distinction. Removing one mechanism does not mean the entire system disappears. It means the system has to find a new way to organize itself, and that is where familiar things begin to look strange. Today, we live beneath large air currents that curve around the planet. Powerful high-altitude flows, such as the jet stream, influence the paths of weather systems. Large-scale circulation cells transport heat between different regions. Ocean currents also form broad circulation patterns across the seas. Many structures like these depend heavily on the fact that the Earth is rotating. If rotation disappears, we should not simply take today's climate map and erase a few arrows. The entire pattern has to reorganize. The familiar ocean circulation gyres would no longer be shaped in the same way. High-altitude air currents might no longer exist in the forms we know. The transport of heat between the equator and high-latitude regions would have to find different pathways. Even tropical storms would become a different story. Today, the Earth's rotation plays an important role in helping large systems organize into rotating structures. If that effect became almost completely absent, we could no longer assume that familiar storms would form and behave the same way they do now. But once again, that does not mean the sky would become peaceful. Energy would still enter the atmosphere, water vapor would still exist. Temperature differences would still create pressure differences. If the sun heated one region more strongly than another, the atmosphere would still have to find a way to move energy away from that region. So after the initial shock, the story of weather would no longer be about air currents retaining their old momentum. It would become the story of a new atmosphere, learning how to distribute heat across a planet that no longer rotates. And here, for the first time since this thought experiment began, we can see a small amount of hope. The atmosphere is not only a threat, it is also a protective system. As long as it can continue circulating, it can carry heat from warmer places to colder ones. The oceans could also participate in that process. The same systems that once produced storms and rain are also the systems that help prevent the Earth from becoming a collection of completely isolated climate zones. But that hope depends on a question we still have not answered. How long would a region of land be heated by the sun? Because to know how hot or cold the new climate would become, we need to know more than just which direction the wind would travel. We need to know how long the sun would remain in the sky. Until now, we have still been carrying a familiar clock in our minds. Morning, Afternoon, sunset, night, then the sun rises again. A 24-hour cycle seems so fundamental that we have almost never thought of it as part of the climate system. But it is exactly the amount of time that land, ocean, and atmosphere are allowed to absorb heat before darkness returns. And when the Earth no longer rotates, that clock does not simply slow down. It completely loses its old meaning. This is the moment when the 24-hour day disappears. But the sun does not disappear with it. And to understand that seemingly contradictory idea, we have to separate two motions that almost no one ever needs to distinguish in everyday life. The Earth rotates on its axis. At the same time, the Earth moves around the Sunday. These two motions exist together, but they are not the same thing. The Earth's rotation is the reason a location on the surface continuously turns toward the sun and then away from it. That is the foundation of the cycle of light and darkness that we call a day. The Earth's journey around the sun determines a much longer cycle, approximately 1 year. In the normal world, these two motions happen at the same time, so seamlessly that we only notice the final result. The sun rises, moves across the sky, sets, and then returns the next morning. But in this thought experiment, one of those two motions has been removed. The Earth no longer rotates on its axis. It continues moving around the Sunday. And that detail creates one of the biggest changes we have encountered since the beginning of this story. Imagine that you are still alive on the surface of this new Earth. After all the upheaval involving the ground, the atmosphere, and the oceans, you look up at the sky. The sun is still there, but it is no longer in a hurry. In the old world, just a few hours could be enough for the sun to move from near the horizon, rise high into the sky, and then descend again. Now its position changes so slowly that you could live through many days while the sky appears almost unchanged. The sun would still move, but it would no longer complete that journey in 24 hours. Because even though the Earth is no longer rotating on its axis, the direction of the sun relative to a location on the surface would still gradually change as the entire planet continued moving along its orbit. It would take nearly one full orbit for the familiar cycle of daylight to be completed. In other words, what we once called a solar day could now last approximately 1 year. This is where intuition truly begins to lose its footing. A morning is no longer a matter of a few hours. Daylight could last for weeks, then months. Only after that would the sun finally begin moving toward the horizon. And when it sets, darkness would not end the next morning. It could continue for many weeks, then many months. But the result would not be exactly the same everywhere. The Earth's axis would still be tilted. Latitude would still exist. The geometry of sunlight would still change depending on the planet's position in its orbit. So different regions would experience the angle and duration of sunlight in ways more complicated than a simple model in which every location has exactly 6 months of daylight and 6 months of darkness. The important thing is not one identical number for every city. The important thing is that the timescale has completely changed. Hours become days. Days become weeks. Weeks can become months. And that leads to a very common misunderstanding. If the Earth stopped rotating, would one half of the planet permanently face the sun, while the other half remained in darkness forever? No, that would be closer to the situation of a planet tidally locked to the sun, where the same side continuously faces the star. But that is not our scenario. The Earth is still moving around the Sunday, so the region receiving the most direct sunlight would not remain fixed forever at the same longitude. As the planet gradually progresses along its orbit, the direction of the sun relative to the surface would also change. A region experiencing months of daylight would eventually move into sunset. A region immersed in darkness would eventually see sunrise return. That is a small but extremely important detail. No place would be permanently condemned simply because it happened to be dark at the moment the Earth stopped rotating. The light would return. You would simply have to wait much longer. And this is where the 24-hour clock, the symbol that has followed us since the beginning of the story, would finally become inadequate for describing the world. 12 hours, 18 hours, 24 hours. The numbers that once organized sleep, work, meals, and almost the entire rhythm of civilization would no longer correspond to the natural cycle of the sky. Instead of asking what time it is, a surviving community might have to ask a completely different question. How many days have we been under the sunlight? Day 10, day 40, day 90. The sun still has not set. And this is not merely a question of when human beings should sleep. Our bodies can use artificial light. Clocks could continue dividing time into 2 4-hour periods if we wanted them to. An underground city could even simulate morning and evening. But the ground outside does not care about human clocks. The ocean does not care, neither does the atmosphere. For them, what matters is energy. A region of land that once received strong sunlight for only a few hours before nighttime arrived and cooled, it could now continue absorbing energy for days and weeks. On the other side of the planet, a region that has lost the sun would not simply experience a longer night. It would continue losing heat without the familiar morning arriving soon afterward. The 2 4-hour clock, therefore, was never merely a tool that told human beings when to wake up. It represented the alternating rhythm of gaining and losing energy that the entire surface of the Earth has lived with for an extremely long time. And now that rhythm has changed, there is one comforting thing about this new world. Sunrise would still exist. Sunset would still exist. No place would necessarily lose the sun forever, but they would become far rarer events, almost like great seasons of light rather than moments repeated every day. And if you were standing beneath a sun that had remained in the sky for many weeks, the next question would become almost impossible to avoid. After weeks without sunset, how hot would the ground become? After weeks without sunset, how hot would the ground become? The first answer may surprise us, not so quickly that everything immediately bursts into flames. Sunrise does not turn a region of land into a furnace within just a few hours. Soil, water, and the atmosphere can all absorb energy before their temperatures change dramatically. This is what we call thermal inertia. You have encountered it in ordinary life. A large lake does not heat up as quickly as a slab of rock under the sunday. And when the sun sets, it does not cool down as quickly as the surrounding ground either. The oceans are the largest example. Their enormous mass of water can absorb a significant amount of heat, while their temperature changes only gradually. The atmosphere also carries some of that energy away from areas that are heating up. Clouds can reflect some sunlight back into space, while also trapping some of the heat radiated from the surface. So the first few days of prolonged daylight over a region might not look like the end of the world. You might still be able to stand outside. The air might still remain within tolerable limits. The ocean would not yet have become one enormous mass of hot water, and that is the danger of slow changes. They do not necessarily tell you right away how far they will eventually go. The first week passes. The sun still has not set. The ground continues receiving energy. Some of that energy is reflected. Some is radiated back into space as heat. Some is stored in the ground, water, and air. If the energy coming in and the energy going out balance each other, the temperature may move toward a relatively stable state. But if, over a long period of time, that region receives more energy than it can release, heat will continue to accumulate. Week 4. The sun is still there. Water evaporates more rapidly in places that are heating up. The air carries moisture elsewhere. Clouds form, potentially reducing sunlight in some areas, while also changing the way heat escapes from the surface. Growing temperature differences create stronger pressure differences. The atmosphere tries to do its job. It transports heat, but it now has to transport heat across a planet where regions of daylight and darkness last for weeks or even months. By the second month, the problem is no longer an afternoon that is hotter than usual. It is an entirely new season of heat. A region of land could receive continuous energy for long enough that the soil gradually dries out. Surface water evaporates more quickly, and ecosystems experience prolonged stress that once occurred only during short heat waves. But we should not fall into the opposite trap and imagine that the entire sunlit side would become a glowing red desert. The oceans would still regulate temperature. The atmosphere would still transport energy. Clouds would still alter the radiation balance. Terrain, latitude, and axial tilt would still cause different regions to receive sunlight in different ways. The new world would not be divided into two simple colors. It would be a constantly adjusting climate system. Then eventually, after a period so long that a sunset might become an event an entire generation of survivors had been waiting for, the sun would begin to disappear below the horizon. And on the side that had just entered darkness, the entire problem would reverse. stored heat would begin leaving the surface. The first day in darkness might still be relatively warm. The ocean would still retain heat. The ground would still release energy it had absorbed. The air would still transport some heat from other regions. But a week would pass. The sun would not return. Then another week. Surfaces with less ability to retain heat would begin cooling more quickly. Snow and ice could appear in places cold enough for them to form. And as the surface became brighter with snow and ice, it would tend to reflect more sunlight when the light finally returned, adding another layer of complexity to the climate. The ocean could delay freezing because of the enormous amount of heat it stores. But delaying does not mean preventing it completely. The atmosphere would also help reduce the difference by transporting heat from warmer regions to colder ones. This gives us an important realization. The hottest place and the coldest place might not be where humans should go. Perhaps the most tolerable region would lie somewhere between them, near the boundary between day and night. There, the sun might sit low on the horizon. A region would not have to endure the strongest sunlight of the prolonged daytime period, but it would not yet be buried deep within weeks of darkness either. It could form a band of relatively milder climate, and for the first time since this thought experiment began, we have an idea that resembles a shelter without four walls. A habitable band on the surface of the planet itself, but it has a problem. The boundary between day and night does not remain still. The Earth is still orbiting the Sunday, so that twilight region would also slowly shift over time. A place that was once comfortable could gradually move deeper into prolonged daylight. Another place that had been growing colder could eventually approach sunrise. If humans wanted to follow a suitable climate, we might have to move with it. In theory, a community with technology and forecasting capabilities could seek out more favorable regions as the boundary of light shifted. Terrain would make this more complicated. Mountains, oceans, deserts, and newly formed coastlines could cut across that path. But the ability to adapt would still exist. Humans could rebuild. Humans could move. Humans could carry energy, stored food, and knowledge with them. And that is the most important glimmer of hope in this chapter. The new Earth might not give us one perfect place to live forever, but it might still give us places that are good enough to continue. The problem is that not every form of life can pack up and follow that climate zone. Think of a field. A wheat plant cannot look up at the sky, realize that darkness will last for 2 months, and decide to move to another continent. Humans can move, but wheat cannot. Humans can move, but wheat cannot. And this is where our thought experiment moves beyond physics and enters biology. So far, we have asked how the ground would move, where the oceans would go, how the atmosphere would reorganize, and how long a day would last. But life does not exist simply because it lives on a planet with a suitable temperature. Life evolved within a rhythm. Light, then darkness. Warmth, then cold. One season, then another. And when that rhythm changes, the question is no longer whether an organism can survive one bad day. The question is whether it can live its entire life in a world that no longer follows the clock its ancestors adapted to over millions of years. Let's begin with plants. Nearly every major food chain on land ultimately traces back to one source of energy: the sunday. Plants use light for photosynthesis, converting solar energy into chemical energy. That process feeds the plants themselves, then indirectly feeds herbivores, carnivores, and eventually us. At first glance, months of daylight might seem like a gift. If plants need light, why not give them more of it? Because a plant is not simply a solar panel. Many species respond not only to the amount of light they receive, but also to the length of day and night. Light cycles help control when plants flower, enter dormancy, germinate, and prepare for the next season. A day lasting for months could disrupt those signals. Continuous light also does not mean photosynthesis would increase forever. If temperatures become too high, water becomes scarce, or gas exchange is disrupted, plants can experience stress even while they are still receiving light. Then, when prolonged darkness arrives, the problem reverses. Some species may enter dormancy. Some are capable of surviving long dark seasons. But many crops used in modern agriculture have been optimized for very specific cycles: planting, growth, flowering, seed production, harvest. Those schedules were not built for a daytime season lasting for months, followed by a nighttime season of similar length. And plants are only the first layer. because a field does not exist by itself. Pollinating insects have to appear when flowers bloom. Animals have to find food at the right time of year. Migratory species need signals that tell them when to leave. Species that reproduce seasonally depend on day length, temperature, and food availability. A 24-hour day does not exist only on human clocks. It is written into the biology of countless species. Inside their bodies are biological rhythms that regulate sleep, wakefulness, feeding, hormones, and many other processes. Even we feel this very clearly. A time zone shift of only a few hours is enough to confuse the human body. Now imagine that the outside environment is not shifted by just a few hours. Daily sunrise and sunset have disappeared completely. Some organisms could adjust. Some species are more flexible than others. Organisms with short life cycles could change across many generations more quickly. Species capable of traveling long distances might follow suitable climates or food sources, but the relationships between them are the part most likely to break down. A plant species might tolerate the new light cycle, while the insect that pollinates it might not. An animal might be able to migrate, while its prey might not follow. Life is not a list of independent species. It is a network of timing. If the links in that network begin operating out of sync, entire food chains could change with them. But even that does not mean life on Earth would disappear. To find places with greater resilience, we should look downward. Below the ocean's surface, the ocean has an advantage that land does not. Water stores heat very well. The deeper you go, the harder it becomes for rapid temperature changes at the surface to reach those depths. That does not make the ocean immune to climate change, but it could make some deep environments more stable than land experiencing months of prolonged heat and cold. And there is something even more important. Not every ecosystem on Earth depends directly on sunlight. In the deep ocean, around hydrothermal vents, there are organisms that rely on chemical energy instead of photosynthesis. Microorganisms can use chemical compounds to produce energy, then become the foundation of ecosystems completely different from those we see on land. Environments like these remind us that life is far more resilient than civilization. Even if many surface ecosystems were drastically reorganized, microorganisms, deep-sea organisms, and highly adaptable forms of life could continue to survive. The new Earth might become a much harsher planet for us, but it would not necessarily become a dead planet. That is a very important distinction. The problem for humans is not whether life in general can survive. The problem is whether the forms of life our civilization depends on can continue providing what we need. One person can survive for a while on stored food. A small group can last longer if they have water, energy, and shelter. But a city is different. A city needs a continuous supply of food. It needs clean water. It needs electricity. It needs medicine. It needs machinery. It needs people who know how to repair that machinery. And a civilization needs even more than that. This is where the thought experiment changes once again. We are no longer asking whether one human being could survive. The answer may be yes. We are also no longer asking whether a few communities could find relatively stable places to live. Perhaps they could. The question is now much larger. How do you feed millions, or even billions of people when the planet's biological rhythms, crop cycles, and climate no longer resemble the world our entire food system was built to serve? And after all the winds, oceans, new maps, and months without sunset, this may be the problem closest to home. Food. After everything we have witnessed, it may be the thing that brings this planet-scale disaster closest to human life again. Because a person does not need to understand the Coriolis effect to know that they are hungry. A family does not need to know whether the oceans have found a new equilibrium to realize that their food supplies are running low. And the first thing we may run out of is not oxygen. It may simply be our next meal. Modern agriculture does not begin when a seed is planted in the ground. It begins long before that, in fertilizer factories, seed production facilities, irrigation systems, agricultural machinery, and transportation networks that bring everything to the right place at the right time. A wheat field may seem to need only soil, water, and sunlight, but to feed a city, that field also needs suitable seed varieties, fertilizer, fuel, equipment, operators, storage facilities, and a supply chain capable of delivering its harvest to millions of people before it spoils. On the new Earth, almost every link in that chain would be under pressure. Extended light cycles would make old planting calendars meaningless. Rainfall would no longer be distributed as it once was. Agricultural regions that were once fertile could become too hot during the long daylight period, or too cold during prolonged darkness. Livestock would not be separate from this problem. Animals need food, water, and suitable temperatures. Their feed also requires farmland. Refrigerated storage needs electricity. Stored food lasts only if we can keep it from spoiling. And then an uncomfortable truth appears. A fully stocked supermarket is not proof that a city has a large food supply. It is only the final point in an enormous system that we normally rarely see. When that system stops, empty shelves are only the final visible sign. To produce food in controlled environments, we would need greenhouses, artificial lighting, water pumps, temperature control, and recycling systems. All of that leads to the second problem: energy. During months of daylight, solar energy could be abundant in some regions. But when darkness lasts for weeks or months, the same solar power system could become an unreliable energy source without enormous storage capacity. Wind would still exist, but wind patterns would have changed. Hydroelectric power would also depend on a new geography of water, new rainfall patterns, and drainage basins that no longer function as they once did. If civilization wanted to survive in the long term, it would need sources of electricity that did not depend entirely on which side of the planet was currently facing the Sunday. Nuclear energy could provide long-term baseload power if humans could maintain fuel supplies, technical expertise, and operational safety. Geothermal energy could become especially valuable in suitable regions. Energy storage systems would need to be large enough to smooth out extended periods when renewable energy sources change dramatically. And an underground city would solve nothing if it could not generate power continuously. Without electricity, artificial lights go out. Without light, controlled environment agriculture declines. Without electricity, water pumps stop. Cold storage loses temperature control. Hospitals lose access to critical equipment. A shelter that is physically safe could become a dark room in a very short time. But energy is still not enough. Humans can survive without food for some time. They cannot survive without water for nearly as long. On the old planet, many cities existed because rivers, groundwater, and rainfall patterns were stable enough to build water supply systems around them. On the new Earth, those assumptions would no longer be reliable. Rainfall would have been reorganized along with the atmosphere. Regions that once received regular water could become drier. Other places might receive large amounts of water at completely different times. Ice could become an important reserve in some colder regions, but extracting and transporting it would also require energy. Groundwater could help a community survive the early stages, but it would not be an unlimited resource. Near the oceans, desalination could provide fresh water, but in return it would require significant infrastructure and electrical power. And so a new civilization would almost certainly have to learn to treat every liter of water as a resource to be recycled. Water would not simply be discarded after use. It would have to be collected, purified, reused. On a small scale, we already know how to do that. The challenge would be doing it for millions of people, continuously for decades. This is where one very appealing image begins to lose its power. The bunker. A shelter deep underground could save a group of people from the dangerous first hours. It could retain heat. It could protect people from extreme weather. But a bunker cannot manufacture turbines by itself. It cannot manufacture medicine. It cannot manufacture computer chips. It cannot mine uranium by itself. It cannot produce replacement parts for a water pump that has been operating for 20 years. A broken filter needs new materials. A generator needs replacement parts. A hospital requires thousands of different pieces of equipment and chemicals. A reactor needs engineers, and those engineers need to be trained by an education system that is still functioning. That is the moment when the problem of survival changes completely. Shelter is not the hardest thing to preserve. Industry is. Civilization is not simply a collection of people who are still alive. It is the ability of someone you have never met to manufacture a component thousands of kilometers away, so that someone else can use that component to keep your city's water system running. If that network disappears, even the most advanced technology eventually becomes machinery that no one is capable of replacing. But that also gives us a glimmer of hope. If humanity can preserve knowledge, energy, manufacturing, and the ability to cooperate, we do not need to recreate the old world exactly as it was. We could build a smaller, more careful system better suited to the new planet. A civilization no longer given the familiar 2-4 hour cycle by nature for free, but capable of deliberately creating its own light, water, food, and living environment. So suppose we manage to do that. Suppose more than just a few people survive. Suppose that after a century, there are still cities, factories, and children growing up who have never known what a natural 2-4 hour day feels like. What would their world look like? What would their world look like? 100 years have passed since the moment the Earth stopped rotating. For those born into this world, the violent winds of the first day are now only history. The oceans that once surged into coastlines no longer carry their original momentum. No one remembers what it felt like to watch the sun rise every morning, because most of the people who knew the 2-4 hour world are gone. But the Earth is still here. And most importantly, the planet is no longer trapped in an ongoing state of catastrophe. It has begun to become a new world. After enough time, the atmosphere no longer remembers the original rotational velocity it once shared with the ground. Friction and momentum transfer have gradually erased the violent differences of those first days. But the air still has one task that cannot disappear: transporting heat. At any given moment, one part of the planet is receiving sunlight for a very long time, while other regions are immersed in darkness. Temperature differences create pressure differences. Warm air still rises. Cold air still moves toward regions of lower pressure. A new circulation system forms. It does not resemble the atmospheric cells, jet streams, or wind patterns that the old civilization once knew, but it has an order of its own. Water still evaporates. Clouds still form. Rain still falls. The water cycle did not die with the Earth's rotation. It was simply reorganized by a world with cycles of light and darkness that last far longer than before. And beneath that sky, the oceans have changed as well. The first waves lost their energy long ago. The water has had time to redistribute itself, according to a new equilibrium. Some coastlines that once appeared on every historical map now exist only in data archives. Old port cities may now lie far from the sea. Regions once considered inland may have become shores of new bodies of water, but the oceans still play a familiar role. They store heat. They exchange heat with the atmosphere. They help slow extreme changes in temperature. The new ocean currents may not resemble any currents we know today, but water still moves under the influence of wind, density differences, and temperature. The Earth has lost one very important regulating mechanism, but it has not lost every ability to regulate itself. And that is what makes the world a century later more than just the remains of a disaster. It is a new functioning system. However, there is still one place we have not looked: inside the planet. Rotation is not only connected to what happens on the surface. Beneath the crust lies the mantle. Deeper still is the outer core, which contains liquid metal, where complex motions help sustain the geodynamo and the Earth's magnetic field. Here, a very easy misconception can arise. The Earth stops rotating, so the magnetic field instantly disappears. We cannot conclude that. The outer core is not a wheel rigidly attached to the surface. The motion of liquid metal inside it has its own dynamics, its own energy sources, and its own timescales. Stopping the rotation of the solid part of the planet would certainly change the conditions of the system. Over sufficiently long periods, the coupling between the mantle, the core, and the Earth's overall motion could lead to deeper changes. But exactly how the magnetic field would evolve in such an extreme scenario is not something we should pretend has a simple answer. And perhaps that is also an important lesson. Science is not powerful because it always gives us a certain answer. It is powerful because it knows where conclusions can be drawn and where uncertainty must remain. While the planet continues changing very slowly, humans have also changed the way they exist. We do not need to imagine flying cities or technology far beyond anything we know. A civilization capable of living on this Earth could be built from technologies whose basic principles already exist. Residential areas could be built deep underground or inside heavily insulated structures to reduce the effects of outside temperatures. Agriculture would no longer depend entirely on open fields. Plants would be grown in controlled environments, where artificial lighting recreates a day-night cycle suited to their biology. Water would become part of an almost closed loop. What is used today would have to be purified so it can be used again tomorrow. Nuclear and geothermal energy could provide baseload power when the surface remains in darkness for months. When excess energy is available during favorable periods, some of it could be stored as electricity or heat for later use. Activity on the surface could also become more flexible. Humans would not necessarily build everything in one place and simply hope the climate remains suitable. Some mining, research, or manufacturing operations could move along with regions experiencing more favorable conditions. The people living in that world might not consider their lives strange. To them, a sun that remains in the sky for weeks would be normal. A season of darkness, lasting for months, would also be normal. Children might learn that their ancestors once lived in an age when the sun rose and set every day, just as we today learn about worlds from the distant past. And that may be the most remarkable thing of all. Humans do not necessarily need an Earth exactly like the one we have today in order to survive. But we do need a system capable of replacing the things the planet currently provides for free. Stable light, clean water, suitable temperatures, food, energy. A new civilization could rebuild each of those things. But every one of them would require knowledge, machinery, and continuous cooperation. After a century, we might still be here. Not because we defeated the planet, but because we learned how to live by its new rules. But the entire world we have just built depends on a single assumption. The Earth lost all of its rotation almost instantly. That is why there was an inertial shock. That is why the atmosphere and the ground fell out of sync. That is why the oceans were thrown out of their old state before civilization had time to respond. So what if we return to the very first moment and change just one thing? Not the destination, only the amount of time it takes to get there. What if the Earth did not stop in an instant? What if the Earth did not stop in an instant? To answer that question, we have to rewind the entire thought experiment. The cities return, the oceans return to their familiar coastlines, the atmosphere stops fighting against the ground, the sun rises and sets every day again. The 24-hour clock once more has meaning. The Earth is rotating as it did before. Now let's run the experiment again. But this time, we change only one variable: time. In the first version, the solid part of the Earth lost its rotational velocity almost instantly. It was that suddenness that created the entire chain of disasters we have just gone through. The ground stopped while our bodies retained their momentum. The atmosphere did not stop at the same time as the ground. Neither did the oceans. In a single moment, systems that had shared the same motion for an extremely long time were forced to operate at different velocities. 1 second, that was the version we just witnessed. And what is remarkable is that much of the initial destruction did not occur simply because the end state was an Earth that no longer rotated. It occurred because the planet was forced to reach that end state too quickly. So let's replace 1 second with 100 years. The Earth is still slowing down. A day begins to grow longer. Rotation weakens little by little. The climate begins to change. The equilibrium sea level also gradually responds. This would still be an extremely serious problem for civilization. But now humanity has something the previous version did not give us at all. Warning: we could measure the decreasing rate of rotation. We could predict how much longer the day would become over the next several decades. We could monitor coastal regions that were gradually becoming less suitable for habitation. Instead of waiting for the water to reach the cities, people could begin moving cities away from the water. Populations could be relocated from areas becoming increasingly dangerous. Agriculture could change crop varieties and farming schedules before the old light cycle disappeared completely. Countries could build more nuclear power, geothermal energy, and storage systems decades before extremely long nights became a reality. 100 years would not make the problem easy. It would only turn a sudden impact into a race. And in a race, preparation matters. But let's give the Earth even more time. Not a century, but thousands of years, then millions of years. Now the story changes at a deeper level. Humans would not be the only ones with time to move. Life itself would have time to respond. When the climate changes slowly, the habitats of many species can shift along with it. Plants can gradually expand into more suitable regions over many generations. Animals can alter their migration routes. Species that cannot adapt may still disappear. but other species would have enough generations for natural selection to begin playing a role in the story. Evolution does not save individual organisms. It changes populations over time. If the environment changes slowly enough, traits that once provided only a small advantage could gradually become decisive for survival. While ecosystems adapt, the solid part of the planet would also have more time to adjust. Water would not have to rush toward a new equilibrium in a single period of chaos. The crust and mantle could respond alongside the long-term change in the Earth's rotation. The atmosphere would not suddenly find itself moving over ground that had already stopped. It would continuously exchange momentum with the surface throughout the process of the planet slowing down. The same destination, but a completely different path. And at this point, our video would no longer primarily be a story about catastrophe. It would become an engineering problem. If we knew that several thousand years from now a day would be much longer, civilization would have to begin building systems that depended less on the current natural cycle. Food would need to be produced in more carefully controlled environments. Energy would need to remain stable, even as periods of daylight and darkness grew longer. Human settlements would need to control their own temperatures instead of depending entirely on the climate outside. Freshwater supplies would need to be protected, recycled, and distributed according to a changing map of rainfall. Migration could not wait until a place became uninhabitable. It would have to be anticipated generations in advance. Industry would also need redundancy. If one manufacturing region disappeared, civilization could not be allowed to collapse simply because one component could no longer be produced. And above all else, there would be knowledge. Because building a greenhouse is not as difficult as preserving the ability to build greenhouses across hundreds of generations. Operating a reactor is not as difficult as preserving the science, engineers, materials, and education systems required so that future generations can still build a new one. When enough time is available, survival no longer depends mainly on thick walls. It depends on the ability to pass capabilities forward. An event that happens in 1 second is a disaster. A change that unfolds slowly enough can become a problem that humanity has a chance to solve. That does not mean everything would be saved. Coastlines would still change. The climate would still have to reorganize. Ecosystems would still come under pressure. A 2-4-hour day could still eventually become a memory. But the difference between being forced to confront a new world in 1 second and having thousands of generations to prepare for it is almost as vast as the catastrophe itself. And perhaps this is the final answer our thought experiment has led us to. The destination matters. But sometimes, the speed at which a world changes matters even more. Because when change happens slowly enough, humans do not merely have time to survive. We have time to understand, time to build, time to pass on what we have learned, and time to transform a changing planet from a sentence into a place where life can still find a way to continue. Thank you for staying with me until the very end of this journey. We began with something so ordinary that almost no one ever stops to think about it. The ground beneath our feet stays still. A glass of water on the table remains calm and level. The sun rises in the morning and disappears when the day comes to an end. There is no engine noise reminding us that the entire planet is moving. There is no signal that makes us wake up every day and wonder whether the Earth is still rotating. Perhaps it is precisely because everything happens so steadily that we easily forget how far from simple that normality really is. Throughout this story, the most remarkable things were not the violent winds, the ocean's changing position, or a world where day and night last for months. What deserves even more thought lies behind all of those things. So many things we take for granted exist only because countless conditions are quietly working together. A day short enough that the ground does not remain hot for too long. A night short enough that life does not have to wait for months before seeing light again. The atmosphere transports heat. The oceans store heat. Water circulates. Plants grow according to rhythms that were established long before human beings ever appeared. And because we were born inside that system, we rarely realize how much it supports us. But perhaps that is also the most beautiful thing this thought experiment leaves behind. When familiar conditions disappear, the humans in our story do not simply try to run away. We begin learning how to live again, finding ways to create light when the world outside is too dark, finding ways to conserve water instead of treating it as something that will always be available, finding ways to grow food when the old agricultural seasons no longer work, finding ways to preserve knowledge so that a generation that never knew the old world can still build something for the generation that comes after them. And in the end, the question is no longer simply how strong human beings are. It is how well we can understand, adapt, and cooperate when the world no longer behaves according to what we once considered normal. Some changes happen too quickly and give us no chance to prepare. But many changes in life happen more slowly. A job comes to an end. A place we once called home no longer feels the way it used to. A plan does not unfold the way we hoped. A chapter that seemed as though it would last forever eventually comes to a close. We cannot keep everything still, but perhaps we do not need to, because human strength has never truly come from the ability to keep the world from changing. It comes from our ability to learn how to live when the world has already changed. Sometimes, what we need is not a perfect answer right away. We may only need a little more time to understand what is happening, a little more patience to find a new path, one more person willing to keep going with us. A change that happens in a single instant can become a catastrophe. But when we have time to observe, learn, and prepare, the very thing that once frightened us can sometimes become a problem we are able to solve one piece at a time. So when this video ends and we return to the familiar room around us, perhaps nothing outside will look any different. The glass of water will still be resting quietly on the table. The sky will still be there. Tomorrow, the sun will still rise, and the earth will continue rotating without needing us to remind it to do so. But perhaps we will look at those very ordinary things a little differently, not with fear that one day they might disappear, but with a little gratitude that, right now, they are still here. Thank you for spending your time with this story. And if there is one thing worth carrying with you after the screen goes dark, perhaps it is simply this. Life does not become precious because everything always stays still. It is precious because, in a world that is always moving, we can still learn how to find our own peace.